orbits of involutions. And so the identity is in orbit, -1 is the orbit, these two are in an orbit, and those two are in an orbit. And so there are 4 cartons. And I've talked about these before. And the split carton only occurs in the sp4. So this whole picture down here, it's the most complicated, interesting part of the picture, all has to do with sp4. If you're on the compact group sp20, there's nowhere to go, it's just a singleton. And the compact group sp02, well, what on earth is that? That's the strong real forms business. That's distinguishing between, I wrote sp20 here. You can think of this, anyway, there's 2 copies of the compact group. And they only contain the compact carton. And then sp11 only has 2 cartons in it, the compact carton and the C-cross carton. So I recommend you look at this picture. Don't look at it anymore. There we go. There it is. It's quite helpful. Questions? Yeah, you need a cross action to get to it. I only indicated Cayley transforms here. So you can get to it by a Cayley transform and then a cross action. Questions?
The arrows are all explained in the algorithm.
Pardon me?
The arrows are all.
Yes.
So what Jeff was just saying is that the Cayley transform entries in the KGP output. What's amazing is that they were able to write this paper before the KGP output was available.
Well, what's amazing is that I was able to make this diagram. Actually, Leslie Saber made it for me. Yeah. All right, let's do something different. So I want to talk about parameters, but before I do that, I had a little digression, which I think is kind of fun. Someone, Dong Chow, asked me the following question. How many involutions are there in the Wahl group of E8? Interesting question for sure. So I'll remind you that the cardinality of the Wahl group of E8 is approximately 696 million. Okay. Yeah, let's do that.
What should they say? $20?
Answer 1. Less than or equal to 1,000. Between 1 and 1,000.
Strict inequalities if you want.
Between 1,001 and 100,000. Between 100,000 and a million. Between a million and 300 million, and the order of those.
So you left out the passage.
Huh?
You left out the passage. Yeah, that's
Boy, it's a tough audience, man. Okay. Okay, so let's see a show of hands. Nobody thinks there's just one. Less than 1,000. There's one. Between 1,000 and 100,000.
Does one need to have a rational reason?
Huh?
No.
Sorry, what was the question?
You need to have a reason for your vote.
Depends what you mean by that.
You need to show citizenship in a
So, sorry, how many here?
Take it down.
1, 2, 3, and 2, 4, and 5, I don't know, 4. 2 of the experts, I'm a little nervous, okay? 100,000 to a million. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 13. It's a big range, so that's greater than a million.
It's a very small range, logarithmically, it's,
Right.
why is it small?
Right. More than a million. More than a million. Fine. More than a million. 0. Huh? Nobody? Okay. All right. So how do you figure this out? So I thought this would be a nice little exercise. I'm going to do it 2 ways. The first way is the brute force way, but just to show you that you can. And this is a little bit of an illustration of what a clumsy programmer can do. I can get things done. When I ask Mark to do them, he's much fancier, but I find it helpful to see the dumb way first. So I want to know how many involutions there are in the Bog group. I'm not going to do E8 because it's too big. Let's do a smaller example. So let's say SP6. So let's say G is equal to SP, or the root datum, or sorry, let RD is the simply connected root datum of type C2. And let's set and W is equal to, generate W of RD. So that's the Bob group. And let's look at it. For W and W, do print this W. So every element of the Bob group is a pair. The first thing is the root datum. It's identifying the root datum, so that's just sort of a tag. And then the second is the product of simple reflections. So the Bob group of type C2 has order 8, and there they are listed. Okay? And if you just want to get the involutions, you just do the following. You say set involutions is equal to the empty array, and then for W and W do, if the order of W is less than or equal to 2, then involutions sharp colon equals W. That says run over the elements of W. If the order is less than or equal to 2, tag it out, append it to the list of involutions by sharp involutions. Oops. 6. For W in involutions, sorry, for blank V in involutions, do this V. So I cut off the root data at the beginning, the identity, the simple reflection, another simple reflection, a conjugate of the first simple reflection, a conjugate of the second simple reflection, and the long elements of the well. That's the elements of order 2 in W. All right? Questions? All right. So this is just an illustration of, the power of the programming language. It has lots of data structures built into it, lots of things, and this kind of question is easy to answer. But I don't want to run this on E8 because it will take too long. And we don't need to run over all of E8 for the following reason. We have the space X, and X maps surjectively onto the involutions in W. Remember that?
In equal rank.
Pardon me?
In equal rank.
Yeah, equal rank case, yep. Twisted involutions in general. And the Atlas knows about X. I guess for X I need the group, so let's say G is the split form of E8. And set, let's do KGB size of G. Wow, that was fast. This has 320,206 elements. So that's an upper bound for the number of involutions in W. So less than 300,000. Everybody's still alive. Okay, but how do we figure it out? Well, I don't want to get too far into this, but let me give you the idea. Let's set C, oh, and actually there's something else that's worth showing here. Let's set C be the Cartan classes of G. Somebody was asking me earlier about how do you see Cartans in Atlas. Here's how you do it. C is the list of Cartan classes of G, and this was I just made a mistake, which is you should never use capital C for a variable, because you're going to come back later and
Not be able to define a complex.
exactly. You're going to anyway. It's too late.
Just
So this group has 10, as David told us yesterday, conjugacy classes of Cartan subgroups. And let's find out about them. So let's do print Cartan info of the first one. It's an array, and the 0 is the first guy. So this is telling me about a Cartan subgroup. I told you that any real torus is a product of S1s, C crosses, and R crosses. And these first three numbers are telling me the number of each. So this is the compact Cartan. It's 8 copies of the circle. And it's telling you that the imaginary roots are of type E8 and the real roots are empty. The complex vector, never mind that. And then there's this other information here which we don't that often make use of, but it's exactly what I'm going to use here. There's this twisted involution orbit size and this fiber size. This twisted involution orbit size is the number that I need. And anyway, so let's look at the next Cartan. So here's a Cartan. The twisted involution is this crazy long fellow. This has 6 compact factors and 1 complex factor. The imaginary roots are type E7 and so on and so forth. And the twisted involution orbit size is 120. Huh?
Are you about to tell us what this involution is?
I thought I was, but now I'm, oh, yes. It's, yeah, that's an excellent question. So, is it a single? It's a single Cayley transform, right? Yeah. So you take alpha simple root.
And the term is simple reflection.
Yeah, it's so it's this alpha. But for some funny reason, the software. So what's going on here is this is the same 120 we saw the other day. The Val group acting on simple reflections. All simple reflections are conjugate. 120, that's them. So in this case, we're talking about the set of S alpha, where alpha runs over the roots, all roots. Modulo plus or minus 1 because you're, that's 120. So I've started counting involutions. There's one identity, and there's 120 of these, and I just have to run over all the Cartans and add up those numbers. And yeah, I could just do it by hand, but I just wrote a little script. Let's see, am I in the right place? Let's do count involutions, set ABC count involutions of simply connected E8. I guess that's RD, but never mind. Okay, so what's the answer? Here are the 10 Cartans, and each Cartan contributes that many involutions. And when you add up those numbers, you get 199,952. I think it's kind of cool. Now, I also returned, the last thing is our representatives of the conjugacy classes. So this array at the end has length 10, and it's a list of representatives of the 10 conjugacy classes of involutions. And that's the one I just showed you, and probably the last one is long element of the Weil group. Yeah, there's the long element of the Weil group.
Another curious question. Which reflection is one? Which group?
That's an excellent question. I have no idea. So what Mark is pointing out is that this conjugacy class consists of all of the reflections. And if a simple reflection, when you write it as a product of simple reflections, is just itself. But this is some, it's probably the highest, no, I don't know what it is. This is a simple reflection. And Mark's asking which, not a simple reflection, this is a reflection. And the question is which root? And that's a good question. Actually, let's do an experiment. Let's set W is equal to C bracket 9, or actually, yes?
So what are those numbers?
What are what numbers?
Type C bracket 1.
So C is a list of Weil group elements. And each Weil group element is written as a product of simple reflections. So the C bracket 0, that's the first one, that's the identity. And C bracket 1, all of these numbers are from 0 to 7. So these are products of simple reflections in type E8.
What's the length?
57, of course.
So it has to be the highest.
All right, so let's set alpha is equal to the highest group of RD. So RD is simply connected to type E8. What? So I think if I do reflection, RD alpha, thank you. Oh no, this is going to give me a matrix. What was this element? C bracket what?
1.
So for those of you who weren't following that, David conjectured or stated without doubt that this reflection that we're getting here must be the reflection in the highest root. And so I computed the reflection in the highest root as a matrix. And that's it. And then I computed the W matrix of this reflection that we're talking about, and these two are equal. So confirming David's statements. Pretty cute, huh? Questions?
Do you or Mark have any idea of the size of the data? When you do this generate W thing, what's the size? How much data is required for each element of W?
Mark?
Well, the representation is reduced point for W.
Yeah, it's a bunch of integer arrays.
Integer array of average times 60.
And how big are the units? So each of the integers is 2 bytes? So it's
Yeah, bytes.
yeah.
Fit where?
The E8 calculation, I think I mentioned.
Oh, you mean just running over the whole vol group?
Yeah.
Oh, I think I've tried generating the vol group V8 on my laptop and just gave up after time. It wasn't a space thing. I think it just was taking forever.
I did E7.
Yeah.
But yet I never tried.
And E7 maybe takes 10 minutes or something?
Oh, I see.
Less?
Last night I tried E6 and generate the random opposite after 10 minutes or more. So E7 I think is maybe 1 minute.
I mean, I've been running Atlas since you mentioned this problem, generating the biological V8 is 15 minutes so far, and it's only up to 43 megabytes in size.
Oh, I see.
According to what you're saying, that's, you know, it's a tiny number of viable companies. I mean, less than a million.
Okay, let's do some good. All right.
I just tried in B to generate W model of a row. It said cannot handle is 696,700 by 8 matrix.
All right, so let's go back and do some very elementary parameter stuff. Set G is equal to SL2R. So when you want to play around with parameters, the first thing to do once you have a group is to just get a parameter and start monkeying with it. So the simplest thing is always to start with the trivial. Let's set T is the trivial. It's a parameter, and there it is. It's parameter 2, 1, 1. So I wanted to say something here. David mentioned this in the context during the Congress talk, and I just wanted to emphasize it. P is a parameter, x lambda nu, is a parameter. That's all it is. It's a parameter. And in Atlas, parameters play 2 roles. Associated to a parameter is a standard module, which is induced from MAN up to G of something, full induced, and also an irreducible representation, which is the unique irreducible quotient of this thing. And depending on the context, P might be standing in for this or this, and you need to be a little bit smart to know. And at some point I started implementing something which would distinguish between the two, but it never really went anywhere. So anyway, so just keep that in mind. All right. So so the trivial parameter is equal to 2, 1, 1. Okay. So let's check what rho is. Rho is 1. So this is KGB element number 2, rho. And KGB element number 2 what's the
What is this? This is a time installment?
yes,
But the two last entries live in different places.
the what?
There are three entries in this matrix. The last two lives in different places. How can
These
you
three
write-
entries?
No, below. Well, how can you write all?
This is row and that's row. There's row, the lambda is row and the new is row. What's the matter?
Lambda is in a quotient of x upper star plus rho. And nu is a different quotient. But the things being written here are representatives.
Is that the question? Yeah, so to be precise, lambda bar is an element of x upper star modulo 1 minus theta x upper star and plus rho, parentheses. And what's theta, by the way? Well, let's check. Let's set x is x of p, or t, excuse me. So that's this KGB element 2. So you can always access these entries by their names, lambda of t and nu of t. And what's the involution of x? That's a 1-by-1 matrix, -1. So that's telling you that theta is -1. So this is x upper star modulo 2 x upper star. And the rho goes away because it's in x upper star. So that's literally what this is. And lambda is an element of x upper star, is a representative of lambda bar. And nu is in x upper star tensor q upper minus theta, which is x upper star tensor q. Okay? And I mentioned this example in my talk. This is the spherical principal series. Principal series of SL2 with infinitesimal character rho. That's another thing I can check. What's the infinitesimal character of this fellow? Rho. So that's what it is. Okay? Now let's check something. This argument here was 1. What if I change that to 3? Let's set p is equal to the following parameter. Use the same x, use 3, and use the same nu. Okay, so what did I do? I said, same x, same nu. I put in 3, and it replaced it with 1. And that's what the software is free to do that. That's this quotient. Okay? And so it's the same, it's literally the same parameter. All right?
So the point is the software does some choice of coset representatives, but it's not necessary for you to know what it's doing. You can put in any representatives you like, but you just need to know that the software is going to change it to its preferred representative in order to be able to tell when two parameters are equal, things like that.
So the other obvious thing to do is to take the same parameter and put in something different mod 2 here, let's say 0. Why did it do that? Its preferred representative is 2, not 0. Whatever, fine. And what's the infinitesimal character of this representation? Of course, rho. You have to look. And so what representation is this?
Just change the sign of this.
Yeah, exactly. So the parameter,
So now it's
this parameter is p, which is equal to x sub 2, 1, is induced from b up to g of sine of x, absolute value of x to the 1. And it's the odd, the k-type, the principal series with odd k-types, principal series of SL2. Okay. And let's check T. I'm getting slightly ahead of myself. I'm going to talk about this another day, but that's what we're doing. So T is a parameter. I'm asking for the composition series of T. The composition series is something you ask about a standard module. So implicit here is you're thinking of T as, this is going to give you the composition series of this full induced module, wherever it is, I don't know the word anymore, the spherical guy. And it has three parameters. It has three constituents. It's reducible, and it has three guys in it. On the other hand, this P is irreducible. All right. Questions? Yeah.
Finite dimensional?
Pardon me?
Are they reducible to finite dimensional?
P?
Yeah.
No, P is infinite dimensional. T is finite dimensional. So what does that mean? Well, if you ask whether something's finite dimensional, you must be talking about the irreducible. That'd be a silly question to ask about the full standard module. So the question is the unique irreducible quotient of the spherical principal series at rho finite dimensional? And the answer is yes, it's the trivial representation. Okay? Now, one of the things that's handy to do is to look at blocks. So I said if you're looking to start messing around with representations, it's convenient to start with the trivial representation. And then the sort of next natural thing to do is to look at the block of the trivial representation, which typically has lots of interesting representations in it. So in this case, the block of the trivial representation has three parameters in it.